So let's review this notation that we use for the function type. So the predicate, there was a domain of the predicate, like a domain of the function. So predicate is going to be a statement. It's a statement that involves variables. So it depends on the variable. So there's going to be a domain for the variable x. So that's going to be called the domain, like a domain of the function, or universal domain of this course. This is the expression, but we call it the domain. So if you change the x, anytime you replace the x by a number, there is going to be a statement. That statement can be true or can be false. So it depends on the x. So we create two famous terms, okay, two famous cases, and we use something we call it quantifiers. So it depends for how many of x's or how many of values of x this predicate of the p of x is going to be true or false. If this is going to be just one number, we call it some number, or there is a one. So if there is going to be, there is a value of x, at least one, such that the p of x is true, so we write this expression. There exists x px. Okay, there exists x px means this px is true for one value of x. Okay, we say there is x px. So that's a notation that exists. And if your predicate is going to be true all the time, means for all values of x in the domain, p of x is a true statement. So we use this expression for all. So that's a notation for all x px. For all x px means we already try all the x's in the domain of the function, domain of the predicate, and we find that the px is going to be true. Okay, so that's what we did the other day. So we should be able to read it, to apply it, this method. So that was the last example that we did, and we are going to give you more, okay? Any question? So let's see what is going to be other example looks like. So we continue with the example here. So we create something and we ask you to rewrite it for us. That's going to be one question on this type of ideas. So suppose always the domain would be given to you, and where is very important. So suppose the domain is z, set of integers, okay, is the set of all integers, So all integers mean we can use 1, 2, 3, 4, 5, 6, 0, and the -1, -2, -3, etc. So that's going to be integers. Now, so what we would like you to do is we'd like you to translate, we call it transcribe, each predicate. We give a predicate in word form, you write it down in symbolic form. Okay, so the expression is transcribing. Okay, that's it. We want you to transcribe each predicate, each given predicate into a logical notation, into logical notation. Okay, so we are going to try some. So let's start with number one, part one. Part one, this is the given one. For each, okay, for each value of x, for each value of x, one can find a value of y such that x plus y is equal to the 0. So this statement is given to you. So what we would like to do, we'd like to write it down in symbolic form using the predicate notation. So you have to identify your predicate statement first. This is it. This is going to be an equation in two variables. So you have to introduce your predicate with two variables, okay? So this is going to be solution. So for your solution, so we're going to do, you're going to introduce, suppose, predicate in two variables, p, x, y. This is going to be this statement. Remember, not equal to, this is just a statement. A statement that x plus y is equal to the, okay, is equal to the 0. That's your first step. Okay, you translate the given information into the predicate notation. Now you have to change it into the, okay, into a quantifier, just using this one, okay? So for the first part, for each value of x, for each value of x means for all value of x, okay? For each value of x, for all value of the x, you know that this is going to be a universal, okay, universal quantifier. So it's going to be for all x, for all x. This is for each value of x. So this is going to be for each value. This is the first one. For each value, one can find a value, one value. One can find one value of y that satisfies this condition. So this means you give me x, I give you y. That's what it is. So for all value of x, for all given one, there exists, you see, there exists a y. There exists a y such that, okay, there exists a y such that px comma y is going to be true. Okay, so this is going to be the translation, if you like, or the solution of the problem. Okay, so first thing to do, you have to identify the statement. Okay, this is going to be the statement, the predicate. It's going to be a predicate in two variables because we have the x and the y. Then the quantifier. As you read in the given order, you are going to put them over here. So for each value of x means for all x. For all x, there exists, one can find a value of y. For all x, there is a y. There is a y, pxy. Means there is a y such that the pxy is going to be true. Any question? So this means you give me x, I give you y. That satisfies this condition. Okay, is this a statement true or false?
True.
True. Very good. So if I give you 5, what is going to be your y?
-5.
-5, very good. Yes, we can do it all the time. So this statement is a true statement. Sometimes they ask you whether this is going to be true or false. Okay, so you just note that, make a note for yourself, not bad to know that, and note that it's true. It's true. You just give me x, I give you y. I solve this equation for y. So y would be -x. Okay, any question? So that's the first one. And these are mostly your assignment in the board. Okay, let's have another one. So read it carefully. There is nothing algebra, nothing involved. You're just rewriting the expressions. So what's going to be the next one? The next one is this one. You see, there is some value of x, some value of x, such that for all value, for all values of y, we have, okay, this time is the product. We have x times y equal to the 0. Okay, so that's going to be the statement that you want to translate. There is some value of x, some value, one value, all of them are just going to be the same, such that for all the value of something is missing here, or value of y, a y is missing. value of y, that's y. For all values of y, we have x times y equal to 0. Okay, so we have to get the statement first, solution. So you're going to suppose, so your statement P of x comma y is this fact that the x times y is equal to the 0. Okay, this is going to be their statement. So this means there is a x such that x times y would be 0 for all y. Okay, there is a special x. There is a special value of x that satisfy this condition for all y. And so we translate it again. There is some value of x means there exists. Okay, this is it. There exists an x. There exists an x such that for all value of y, for all y, p of x, px comma y is going to be true. Okay, there is some value of x means there exists x. Okay, there exists x such that for all y, p of x and y is going to be true. So there is a special number, if you like. There is a special number that satisfies this condition that if you multiply by any other number, the result would be 0. Any question? Okay, is it true or false? Can you find a number x such that?
It'd be true and x is 0.
Excellent, yeah, that's it. Yes, it's true, x is 0. Because if you multiply any number by 0, the result would be 0. So again, it's true. It is going to be true. Okay, you can let x to be equal to the 0. Because it's, remember the domain is the all integers. Since the domain is all integers, a 0 is available. If the domain was a counting number, you don't have it, because 0 is not part of the counting numbers. But this is it, the domain was integers. So yes, there is a specific element 0, such that if you multiply 0 by any other number, the result would be 0. Okay, any question? Let's have another one. Then we have quite a lot of these in your practice one. I'm going to post for you later tonight. Practice test number 1. You have various statements. So another one is this one, part C, different format. This is it. There is, okay, there is some. There is some value of x, some value of x, and some value of y, and some value of y. Okay, both of them are going to be there exist, for which the product x times y is equal to 15. Okay, there is a value of x and there is a value of y such that when you multiply them together, x times y would be also equal to the 15. Okay, so your statement is going to be x times y equal to the 15. So you have to create a statement first. So it's going to be solution. So the statement px comma y means x times y is equal to the 15. That's a predicate to start with. Then you just read this expression and just bring the proper quantifiers. There is some value of x. There is an x. You see, there is some value of x means there is an x. And there is some value of y. There is a y. There is an x and there is a y in the domain of the predicate such that p of x comma y is going to be true. So this means there is a value of x and there is a value of y such that if you multiply them together, the result would be 15. Okay, is it true or false?
It's true.
It's true. What is x and y?
You can use x is 3 and y is 5.
That's it. Yes, x3 5. X1 by 15, because the 15 is 3 times 5 and it's also 1 times 15. So we have many choices over here. Okay, so yes, it is true. It is true. Let's say we had x equal to 3 and y equal to the 5, for example. So if they ask, as it is in your assignment, if they ask whether it's a true or false, so then, you just answer that one. Otherwise, you're done. Okay, any question? So that's, that's how you work with the predicate and you put them together. Now, the important part is the next one, the next result. This is covered in 3.2, but we do both of them together. The important part is what is the negation of these quantifiers? Okay, that's going to be the one, and this is the one that we're going to use for the rest of the course, if you like. So the next one is going to be, just bring up this, that one. Okay, so the next one is 3.2. Okay, the 3.2, and we want to see what is going to be negation. Okay, so that would be negation. Okay, what's going to be negation? Negation of a quantifier, Negation of a quantifier. And most of the time, this is the one that we're going to use in different, okay, to take care of different theorems. Just have a, okay, there you are. Remember, we have two types of quantifiers. Okay, there exists and the other one. So we're going to check each one of them to see how we're going to write the negation. Okay, that's it. This is number one. Number one, the question is, what is the negation of this statement? The negation of for all x. Okay, the negation of for all x px. Okay, that's it, for all x px. You want to find the negation of this one. Okay, so this is going to be the question. Okay, now how are we going to get this question? We just read it to see what does it mean really. Okay, so you want to find the negation of for all x px is true. So when we start with this means the negation would be what? This means it's not the case. It's not true. It's not true that p of x is true for all value of x. Let's write it down as I talk about it so that you can see it. You see, note that, you just check to see what's the meaning. Note that the negation, okay, the negation of this proposition, the proposition that for all x, okay, for all x px is simply this, is, okay, is what? Is that it is not the case, or is not true. Okay, is not. Is not the case, or is not true. Is not the case that, not the case that the p of x is going to be true. Okay, it's going to be true for all values of x. Okay, that's the meaning of negation of that statement. Okay, so it's not the case that the p of x is true for all values of x, which is equivalent to the what? It's going to be equivalent to the fact that there is a value of x. There is a value of x for which p of x is going to be false. Okay, so when we say it is not the case that it's not true, it's not the case that the P of X is true for all value of X, this equivalently means, you see, equivalently, okay, that's it. Equivalently, this means there is some value of X or a value of X, some value of X, okay, there is some value of X for which P of X is not true, is not, okay, is not true. See, these two statements are going to be the same as each other. So what does it mean? So this means there is some value of X means there is an X. There is an X such that what? There is an X such that Px is not true. Px is not true means what? This means Px is going to be false if yes. So there is an X such that not Px. You see? When we say that the Px is not true, this means the negation of the Px is true. So there is some value of X for which P of X is not true. So there is a value of X such that not Px. That's it. So what we prove a great theorem. You see? We prove this one. We prove that the negation of the for all X Px is equivalent to, okay, this would be changing to there exists X. This is it. There exists X. There exists X such that there exists X not Px, not Px. This is going to be the negation of the universal, okay, universal quantifiers. It's very easy. When you want to negate it, you just change the quantifier. This is going to be for all. So the negation would be there exists X. And the negation of the statement, whatever it is, okay, it's going to be Px. You just consider not Px. Any question? You see, nice proof. So you don't need anything else. This is just reading the argument and change it to it. So we start with the fact that this means not that is not that. You see, not that for all X Px is true. Not that for all X Px is true means it's not the true that it's not the case that for all X Px is true. So this means there are some values. There is at least one value of X for which P of X is false. When the P of X is false, the negation is going to be true. So that's it. So the negation of for all would be there exists X not Px, and we do the same thing to get the similar one. You see, similarly, same idea can be used to prove that the negation of there exists X Px is going to be equivalent to, so we change there exists into for all, and we just use the negation of the P of X. That's it. So that gives you the negation of there exists. So basically, if you want to negate a given quantifier, so what you do if there is going to be for all X, the negation for all would be there exists, and the negation of there exists would be for all. And then you have to switch the statement from the Px to the negative Px. That's it. Any question? If you think about it, this is the De Morgan law. That's exactly what you did with the De Morgan law. You're just using the De Morgan law for two cases. You see P or Q. This is more than that, but that's easier interpretation of this theorem as I did it. So you don't need to any other justification really. Any question? On the test, some people miss the point, you see. They miss the fact that, remember, it's two parts. The first part is a quantifier. you switch the quantifier. You switch the quantifier, but there is a second part. You have to negate the P of X. Some people write there is X, PX. No, it's going to be, this is the quantifier, the actual one is the PX, that you have to change it to the negative PX in both cases, okay? And otherwise that we are done. And that's it. We are going to use it for the proving the theorems in the next chapter, quite a lot. But for the time being, we just give you some expressions, and then you are going to find the negation of those expressions for us, okay? Most of them are easy. As usual, if it's going to be conditional one, this is the one that sometimes you missed. So be careful, otherwise we're done. Question? So let's practice how we're going to apply it. There you are. So example. We want to find the negation of each statement. There you are. Find the negation. Okay, find the negation of each statement. Each statement. Okay, so the statement but given, you are going to find its negation. So let's go with the first one. Okay, that's it. The first one. The first one, this is the expression that we're going to have. So you be given for all x, x squared is less than 0. You want to find the negation of this one. Okay, so this is going to be your P of x, the statement. So what you do, you negate the quantifier for all would be that exist, and then you switch the, okay, you switch the P of x. So this is going to be your solution. And this is the way you write it down for me. Okay, that's it. You say, I want the negation of this one for all x squared less than 0. So it's equivalent to, for all would be changed into the there exists x. There is an x such that, now you have to switch this one. That's a P of x. You have to give us a not P of x, the negation. So it's going to be x squared. So that give x squared greater than or equal to the 0. And you're done. Any question? So we switch the quantifier. Okay, switch the quantifier and negate the given statement. And you're done. That's the first one. Okay, give you another one. Something with 2 variables. So we want to negate this one. For all x, there is a y. For all x, there is a y such that x plus y is equal to 1. You want to find the negation of this statement. So the solution is going to be, so you start with the given one. I want to negate this statement. For all x, there is a y such that x plus y is equal to 1. So it's going to be equivalent to, any suggestion? What's the result? Anybody want to try?
There exists an x for all y. Such that x plus y is not equal to 1.
That's it. Yes, very good. Not equal to 1. So the quantifier would be there exists an x such that for all y, x plus y is not equal to 1. That's it. Okay, because remember, we switched the quantifier, we find the negation of the quantifier, but we have to find the negation of the statement. The statement was x plus y equal to 1. So the negation would be x plus y not equal to 1. Then it's done. Any question? Let's have another one. Oh, this is the tricky one. This is the one that most of the people missed it on the test. Let's see. See, this is the statement for all x and for all y. when x is greater than y, that would implies that x squared is also greater than y squared. Okay, that's going to be the statement that we're going to have. Okay, so let's check if you want to give us a solution. So this is what we are interested in. We are interested in the negation of this statement. For all x, for all y, whenever x is greater than y, then x squared is going to be greater than y squared. Okay, this is it. This is going to be equivalent to, okay, any suggestion? You want to try this one? You switch to quantifier and then you have to find the negation of this. Okay, remember this is if P then Q. If P then Q. And we already talked about the negation of if P then Q. Any suggestion? The quantifier is easy, we know that. This you just switch. Okay, so let's switch this. That gives us there exists an X. Okay, and there exists an Y. This is the quantifier. Now what would happen to this one? Any suggestion? Remember, it's just conditional proposition implications. If P then Q. Remember what was the negation of the if P then Q? You had it in your previous quiz.
P not Q.
P, but not Q. Yes, very good. Yes. So what's going to be this one now? So there is a X and there is a Y.
Such that x is greater than y, then x squared is less than y squared.
X squared is less or equal to.
Less or equal.
Yeah, yes, very good. You say it's if P then Q. If P then Q. So there's going to be P but not Q. Remember, P but not Q. So this means there is an X, there is an Y such that X is greater than Y. Okay, X is greater than Y, but not and the negation of this one. X squared is less than equal to the Y squared. So that's the one. Okay, I just remind you again, this is very important. I've used it before. You see, recall that. This is what we used. The negation of if P then Q is equivalent to what? Is P and not Q. So we're just using this fact. Okay, we use it all the time because the quantifier, we just switch it. The quantifier we switch, but for the implication, it is a conditional. Okay, it's going to be a conditional implication. Okay, so this is it. So we change it. It's going to be there exists and there is y, there is a x, there is a y such that x is less than, x is greater than y, x is greater than y, but or and switch this one. X squared is less than equal to the y squared, and you're done. Any question? Otherwise, the rest are easy, you know, those equations there, but make sure you get this one right. So I give you another one of this quantity so that you know it. So let's call this one number 4. Again, you have a list in that practice test that we're going to have, and quite a lot in your book. So let's check this one. The negation of for all x, if x is greater than 2, then x squared is greater than 4. Okay, for all x, if x is greater than y, x squared is always greater than 4. So the negation is going to be, there you are, solution. Again, you start with the question and you have to write the negation for us to see. You want to find the negation of for all x. If x is greater than 2, then x squared is greater than 4. Okay, equivalent to, so what's going to be the result? Result, we want to try.
There exists an X
There exists an x. Yes.
x is greater than 2 and x squared is less than or equal to 4.
See it, yes, very good. X is greater than 2. You see, X is greater than 2. But or and X squared is going to be less than equal to 4. Okay, so that gives us the negation of the given quantifiers. Okay, any question? So that's it. We are done with chapter 3. In your book, they talk about quite a lot. If you like, you can read it. But the basic part is the one that we talk about it. This negating this, and we are going to use it. Any statement of the proof of the theorem in mathematics would involve this type of expressions, and we're going to check a couple of them to see what's going on. Okay, any question? So we are done with chapter 3. Okay, let's see, we get a couple of chapter 4 too. Chapter 4, very important one. Okay, so what we did so far, we just create a language. Okay, we created a language. Our language is going to be logic. Okay, alphabets are propositions. We make a sentence just using those connective or and. We talk about when an argument is going to be valid. And the other part is we can use quantifier and just, negating the quantifiers. So now what we are going to do, the next step is we are going to build a mathematical system. Okay, we build a mathematical system. Then with that system, we can build up theorems and just continue. Okay, so let's see what is going to be a mathematical system all about. Okay, so we're done with chapter 3. So we are ready to create this chapter 4. In chapter 4, we may get just a couple of these, or just at least one section, just for the test. So this is going to be 4.1.
Sorry, did we go through 3.3 or 3.2 in chapter 3?
No, it's just 3.1 and 3.2 would be enough.
Okay, thank you.
The other one, you can read it for yourself, but we don't need them.
Okay,
so,
thanks.
Yeah, I think that's clear. So we get to the 4.1. 4.1 or chapter 4, quite interesting one. So we have the tools now. We're going to see how we're going to apply it. So this is, let's talk about a mathematical system first. Okay, so what is a mathematical system? We are going to create a kind of a structure, then we work with mathematical system. You see, every mathematical system should have the following parts, if you like, that I'm going to talk about it. We are going to have, sometimes we call them axioms. Axioms are going to be, for your system, is something that you believe they are true. Okay, no argument about those. You have to accept something for your system that's there. So it's going to be axioms. Then there are definitions. So what you're going to do, you're going to define something to be able to create something new from the old one. So you have the axioms, they are all there. So we get the definitions. Definition is going to be something that we use to create something else. Okay, then you're going to have theorems. Theorem is going to be a proposition that we are going to create. Okay, proposition that we are going to create, and we try to prove that they are going to be true. In order to prove, we need a method of proof. What is the method of proof? It's going to be a kind of argument that you're going to use, using some definitions, some of those theorems about the proposition that we talk about it to build up this. Okay, so these are going to be the foundation of the argument. So let me just list it for you. A mathematical system. That's it. So what is a mathematical system? A mathematical system. Okay, mathematical system consists of the following. Consists of the following. Okay, the following. The first thing that we are going to have for each system is axioms. axioms. These are some expression that need not to be proof. Just believe in it. Okay, this is going to be the axiom of our system. Okay, so these are going to be propositions. Okay, these are going to be propositions that are assumed. Okay, are assumed to be true. To be true. So these are called axioms of each system. We have some of these ideas. Okay, that's the term axioms. The other term is definition. Okay, the definitions, which is very important, something that we create, we define, and then we can use it to get something new. Okay, so what's going to be definitions? So the definitions are going to be, see the definitions. Definitions are going to be used to create something new. To be used to create, okay, to create new concepts from the old one. New concepts from old ones. From old one. That's definition. Okay, you define something and then you continue. Okay, you create something new. That would be definition. In some systems, there are going to be some terms that you may need it. So you are going to call them undefined terms. So a system may have some terms that we call them undefined. Okay, it's going to be undefined. Undefined terms of the system. Okay, so this, something like a corresponding. Okay, if you like, they are going to be corresponding to the primitive concept, if you like, to the primitive concepts of the system. Depends how you define your system, and then you may have some undefined terms of the system. So these are going to be undefined terms. Now the important part is going to be theorems. So you build up a system, then you predict something, okay, something that may be true or may be false, but you have to prove it. That's why we call it theorems. So the theorems are propositions, most of the time conditional one. So these are going to be propositions. Okay, there's going to be propositions that can be proof. That can be proof. It can be proved to be true. Okay, these are the ones we call them propositions. We call them theorems. Okay, you create something and you claim something, and then you are going to prove it. The important part is a proof. So what is a proof? Okay, a proof is going to be a method. Okay, so a proof is going to be an argument. This is the important part. It's going to be an argument that we're going to build up, okay, that establishes the truth of your table, of your theorem. Okay, that's it. That would establishes the truths of your theorem. The truth of a theorem or of a proposition. Of a proposition. Okay, so this is what we are going to call it a mathematical system. Okay, so mathematical system would have some axioms, some definitions. Okay, we put definitions together. You are going to build up or create a theorems, and then you need a proof to be able to, okay, to show that your theorem is going to be true. Okay, any question? Now, there are going to be various examples that we can apply. Okay, so what we're going to do is we are going to, because you may not have a very, or you don't supposed to have, okay, a very deep background, if you like, in different topics to be able to get through this one. So what we're going to do is whatever we need, we are going to create it. Okay, and then you have to apply those one to be able to get through it. Okay, so we are going to focusing on numbers because the numbers are easier to work with, and this is the one that you may have to do in future. Okay, so I give you everything that I need or we need to get through it. First thing, I give you an example of some definitions, and then you are going to use this definition through the course. Okay, so example, these are going to be examples of definitions. Okay, so definitions. So these are a standard. You can use it anytime you like, but you have to use it in the following format that I'm going to write. Okay, there you are. I want to define even and odd number for you. So this is going to be the definition of even and odd that you have to use in this course. There you are. If n is an integer. If n is an integer, then n is going to be called even. N is even. You know that the definition for the even is going to be, this would be a number that's going to be divisible by 2, or it's a multiple of 2. So this is how we define it. We say that n is even if there is, okay, if and only if there is, okay, there is an integer, okay, there is an integer k such that n is equal to the 2k. That's a definition of even number in this course. Okay, if you say n is even, this means there is a k such that n equal to the, okay, n equal to the k. In short form, this is the way you write it down. Equivalently, and you need it quite a lot. Equivalently, this is the way we write down in short form. As soon as we say, oh, n is even if and only if there is a k integer. There is a k such that n is equal to the 2k. This is the one that we're going to accept for the even numbers. Any question? So you know that the number is even is divisible by 2. If it's going to be divisible by 2 means it's a multiple of 2. So that's why 2k is a multiple of 2, okay? So for example, 6 is 2 times 3, so k is 3. But if you have 14, it's 2 times 7, so k is 7. So always you can find the k such that this condition happens. So this is going to be the one that you consider for the definition of the even number. For the odd numbers, you are going to use this one. Similarly, okay, similarly for the odd number, n is going to be odd. Anytime you see n is odd, if and only if there is a k, such that n is equal to 2k plus 1. So that's the definition of the odd numbers. Okay, for the even number, as far as we are concerned, that's going to be a multiple of 2, n equal to the 2k. For the odd number, it's going to be n equal to the 2k plus 1. We accept only these two as a definition of the odd and the even number, nothing else. Okay, any question? Let's get practice. You have some problems in your book. I just want to show you that They are problems, and then you have to solve it. And this is how we're going to solve, because you have to be precise. And this is anything we talk about in this course. Either it's we already proved it, or we have to prove it. Okay, so we don't believe in anything outside of this course from now on. Okay, so this is the way we are going to operate. Any question? Let's give some examples to get a feeling of how we move and how we work with these. There you are. These are in fact the problem of this section. Let's see. Example. That's going to be example. So what's the example number one? Example number one. This is it. If A and B. If A and B. If A and B are integers. Okay, we wanted to show that - 6a squared b is even. That's it. Remember, even from our point of view is what? It's going to be even if there is a k such that this number can be written as a form of the 2k. That's the only thing that we accept. Okay. Any suggestion? How are we going to write this one as the form of the 2k? Let me explain this one for you just to know what I'm talking about. You see, this is going to be the result. And this is 6a squared b. Remember, you want to write it down as what? Of the form of the 2k. You pull out the 2. It's a 6. 6 is 2 times 3. So we can write down as a 2 times 3a squared b. You see? So a, b, they are all integers. They are going to be all integers. So what you can do is you can call all of them to be k. So if you call it k, so what you have? It's going to be of the form of the 2k. Okay, 2k. That's it. So what you did, you proved that I can find a k such that 6a squared b is equal to the 2k. So according to our definition, so 6a squared b is even. And you're done. Any question? This is the way you proved. Okay, if you bring any other explanation, okay, we are not going to accept it because we have a mathematical system. You see, we decided that the definition of the even number in our system is any number of the form of the 2k. So you have to create the 2k for us, okay, to get the number. Okay, any question? That's the first one. So you have some in your book, and this is the way you're going to answer it. Let's have another one. Okay, how about this number 2? Number 2. What's the number 2? The number 2 is that if A and B, if A and B are integers again, are integers. Okay, if A and B are integers, we want to show that. Okay, show that this is going to be the case. Let's bring this one a bit better. Okay, we want to show that 10a. Okay, show 10a plus 8b plus 1 is odd. Okay, that's going to be the one. So A and B are integers, okay? A and B are integers. We want to prove that this number, 10a plus 8b plus 1, is an odd number. Remember the definition of the odd? Definition of the odd is a number of the form of the 2k plus 1. Any suggestion?
Factor out of 2 from 10a plus 8b, so you'd have 2 times 5a plus 4b plus 1. So k would become your 5a plus 4b plus 1.
Yeah, excellent. That's it. Yes, very good. Yes, that's it. So the solution is going to be, this is the 10a plus 8b plus 1. We factor out the 2 out of these because we need that factor 2 times. So the result would be 5a plus 4b plus 1. They are all integers, 5a, 4b. We add them together integers. So what we're going to do, we're going to call this one k. So that gives us a 2k plus 1. So you can then say, oh, I did it. There is a k that I give you such that 10a plus 8b plus 1 is 2k plus 1. Just explaining, you know, even this would be fine. So 10a plus 8b plus 1 is what is going to be at, and then be done. Okay, so this is going to be the case. Okay, any question? So this is going to be a case that just any question. So you know, this is the type of operation that we're going to use, so don't be surprised. Give you another one. Number 3. Number 3, if n is an integer, okay, if n is integer, then 2n plus 11 is odd. Remember, the odd number is the number of the form of 2k plus 1. Any suggestion for this one? How are we going to change it into the form of the 2k plus 1? Any suggestion?
Can you separate it and make it 2n plus 10 plus 1?
Excellent. Yes, that's where we do it. Yes, very good. Yeah, we need the 1 as to be isolated. So we borrow the 1 from 11, the leftover will be 10, then it's a factor of 2. Yes, very good. So this is it, solution. So the solution is going to be, we have the 2n plus 11. Okay, it's going to be 2n. You isolate that one, 2n plus 10 plus 1. Okay, so out of these, we are going to factor out the 2. So that gives us a 2 out, which is going to be n plus 5 plus 1. Okay, now n plus 5 is an integer, so we can call it k. So that gives us a 2k plus 1. 2k plus 1, that's it. So you can say that, oh, I did it. So I proved that there is a k. There is a k such that 2n plus 11 is equal to the 2k plus 1, and that's it. So 2n plus 1 or 2n plus 11 is going to be odd, and be done. Okay, so I think the idea, the type of things that, you know, we are going to do in this, you know, in this course or from now on to get these numbers. Okay, any question? I'd like to give you one of those method of proofs that we have so that we can have this one for the test. Okay, this is a kind of section 4.1 if you like. But the big thing is that part of the proof. Okay, the question is, so these are the definition. Okay, we use the definition to get this. So the question is going to be, we can use this definition to make theorems. Okay, we can make a theorem. For example, the theorem is the sum of 2 even number is even. So this is a theorem that you have to prove it for us, okay? or the sum of an even number and odd number is odd. So the question is going to be, how are we going to prove this theorem for us? There are 4 different methods of the proving the theorems, and let's talk about one of them. Probably we won't get time to do more, but it's not bad to get one of them on this test. So this is going to be methods of proof. The first one is going to be called direct method. So I'd like to talk about this one only, then we finish it. Okay, so you have something, then we leave the other for your next test. We won't get time. Okay, so methods of proof. There are some methods that we call them direct, and some method we are going to call them indirect. Direct method is you start with a given something, you work on it, and you get the result. So that's going to be the first method. There is something we call it contradiction method, a contrapositive method, counterexample. We talk about those one later on. So let's see if we can get at least one of them today, okay, and for this test. So the first method is going to be direct. Direct proof. What's direct proof means? You see, if you want to prove a theorem, your theorem is always if P then Q. That's one. For example, in calculus, you want to prove that if a function is differentiable, then the function is continuous. That's a theorem. If you want to prove it, you have to start with a given information. The information is the function is continuous. The function is differentiable. Then you try to prove the continuity. So what you do is you start with the given information, then you may use some theorems, definition, proposition to be able to get through it. So in calculus, you have to write the definition of differentiability, if you like, to be able to get through it. So basically, this is how we are going to do the direct proof. It's 2 steps. Step 1, write it down nicely. Okay, so this is going to be a step 1. You are going to express or think about it. Express the given statement. Okay, express the given statement. The given statement to be proved. Okay, to be proved in the following format. In the following form. Following form. What's the form? It's just implication. You want to prove that for all x, px implies qx. That's it. This always happens. When you have something, you have to use it and get the second one. So what you do, you pick an x with the property that the px is true. Then use some definition, okay, theorems, put them together to get to the qx. You're not going to go somewhere else in this part. Okay, you have to rely on the given information only. So the part 2 is going to be, you're going to select, okay, select an element x for which an element x for which p of x is true. You assume this. And we're going to show that qx is also true. And show that qx is also true. Is also true. How? By using definitions. Okay, definitions, theorems, definition, theorems, and some rules. And the rules, okay, the rules that we know it, the rules of logical arguments. You have quite a lot, you know. Sometimes you may have to use the Demogal law to get, you know, to get these numbers. But we are ready for all of them. Okay, so that's, you know, this is the direction that you usually apply. This is the way you prove the things. Okay, but you may not realize that you're just using a method that we call it a direct proof. Okay, so I'm going to give you a couple of examples to see how we're going to do it. Again, you don't need any information out of this course, any information. We just rely on the what we defined, and we're working with the numbers so far. So you must know that what's the even number, the odd numbers, so this type of ideas, nothing else. Okay, so the first one is in fact a quite interesting one. That's it. They are going to give you instruction, but for the time being, you don't have any other methods, so you have to know that, you know, that you use the direct proof. So we want to prove this one, you see, prove that the sum of two even integers is even. You may say, oh, it's clear. No, it's not. You have to prove it, remember. The sum of two even integers is even. You want to prove this one. Okay, this is the direct proof. Are you ready? This is how you prove it. Remember, you start by picking two even integers. So that's it. I'm going to tell you what you have to prove. So you can say that these are for your information. One should prove, or you or I should prove. One should prove. You change it to the symbolic form first. One should prove that if M and N are even integers, then M plus N is also even. You see, you change it to the symbolic form, or just right away assume that M and N. This is just for information. You talk to yourself that, you know, I have to do this one. So the starting of your proof is going to be, you are going to pick one of these. You see, select. You're going to select. So this is going to be your starting point, which is important. I write down this color. So you are going to suppose it's given to you. Suppose M and N are even integers, are even. You see, that's your assumption. Now you continue. Get the definition, show that M plus N is also an integer, okay? So the way we're going to do it, remember definition, M is even. Remember the definition means there is a K such that M is equal to the 2K. That's the definition of the M to be even. N is also even. N is even. There is another K. You see, since you want to do two, you cannot use K for both of them because the numbers must be different. So you go back and you call this one K1, 1, and now you're going to say K2. This is one of your common mistakes. You see, if there is only one number, you can call it K. But if you have two numbers, you cannot say that M equal to 2K and N equal to 2K because they are not equal to each other. So that's why you have to use two different indexes, okay? So N is even, means there is a K2. such that n is equal to the 2k2. Any question? That's a definition. What do you want? You want their sum. Add them together. So this means if you add them together, this means m plus n is equal to what? 2k1 plus 2k2. But remember, you want to prove that m plus n is an even number, and it must be multiple of 2. So what do? You factor out the 2. So this is going to be equal to what? Is equal to the 2 times k1 plus k2. But remember, k1 and k2 are integers. So k plus 1, k1 plus k1 is an integers. k1 plus k2. So you're going to call this one, you can call it k. So you arrive at 2k. So what you did, you prove that there is a k. There is a k such that m plus n is equal to the 2k. That's it. So m plus n is even. And you're done. You see? Nice proof. So this is how you nicely prove the fact that the sum of 2 even integer is going to be even. Any question? So you have to assume, you have to pick 2 numbers. Okay, we pick the numbers m and n, and you assume that they are even. As soon as you get the even, you write the definition of the even number. A number is even if it's a multiple of 2. Okay, so we usually say there is a k, that's m equal to 2k, but you have to do it, you want to do it twice. So you have to have 2 different numbers. Okay, you don't have to call it k, you can call it anything else, you can call it t, but I usually go with the k. So it must be k1 and the k2 because you want to use it at the same time. So that's going to be, there is a k1, m is 2k1, n equal 2k2. Now you add them together. You add them together, you want to prove that the sum is also even number. It must be a multiple of 2. So you factor out the 2, you get a k1 plus k2. It's an integer, you call it k. So you get m plus n equal to 2k, so m plus n is also even. So nicely you prove that the sum of 2 even integer is even, and we're done. Any question? This proof is given to in one of your assignments in your book, but they use k and k here. And they ask you what is wrong with that proof. Okay, the wrong is going to be, you cannot use the same k here because they are not different. They are not equal number. You see, if you use the same k, that give m equal to 2k and n equal to 2k. So m must be equal to the n. So you didn't prove it. You just prove it for some special case that m and n are going to be the same. So in this case, that's it. So we prove that the sum of 2 even integer is going to be even, and then you're done. Any question? So the direct proof is not bad, is not difficult. I give you another quick one, and we close it. And this is where we are going to give you the test. Okay, I just wanted to, because there are 3 more methods, but it's not bad to get one of them, to get to this definition. Let's give you quickly another one, and then you check the practice test, number 1. I finish your quiz over the weekend, so on Monday weekend, I post a solution for you. You can talk about that quiz if you like, and then we are not going to review that quiz. I mean, on your practice one, you will see only the new problems. Okay, so we go over those new problems on Monday, and we give you the test on Wednesday. So we have 1 week to prepare for it. Let's take another one. You need this type as well, and they're not matched. You can do with this method. So don't worry, the other methods, there are quite a lot to do. If n is even, okay, even is it's even integer. Then we want to prove that n squared is also even. That would be very useful. You can use it in future anytime you like. 2 squared is 4, for example. You see, 4 squared is 16. So there you are. You want to prove the square of an even number is even, like we did for the other one. There you are, solution or proof. Okay, again, you pick the number. You are going to suppose your opening statement must be this one. Suppose n is even. Is an even or an even integer? We work with the integers only, of course. That's it. Bring the definition. What does it mean? This means there is a k such that n equal to the 2k. I just use the k because I have only one number. What do you want? A square. Square it. So what's going to be the square? N squared, 2k squared is equal to the 4k squared. Remember, you want to prove that n squared is even, so you need a 2k. So what you do is, you can pull out the 2. The left is going to be 2k squared. So 2k squared is an integer. You may call it k. Sorry, you may call it k1. You cannot use the same k. So that give it 2k1. There you are. So what you did, you proved that, oh, there is a k1 such that n squared is equal to the 2k1. So n squared is even. And you're done. You see, very nice proof, very easy proof. Again, you know, we are not going to give you a theorem from calculus, geometry, etc. In future, if you have something, especially in your own field, and you have to apply this method, so you know what's going on. So that's why we just stay with the odd and the even numbers only. That's it. Any question? So we are up to the something like 4.2 for that test. There are 4.2 is very dense section, but in your book the way they cover this chapter 4 is very strange one. They repeat these arguments over and over and over. So you better read your lecture notes first, because that will be short and direct to the point, and then you go back to your book if you want to study, okay, the topics related to this one. In that case, you know, you'll be ready for it, but you have to wait to get the other ones. Okay, that's it. Any question? So look at the take-home trees. This is it. A practice test number 1. I have to drive to the university for my class, but when I come back tonight, I will post the practice test number 1 for you, and we go over all solutions. We get time to do it. Okay, that's it. Any question?
Did you say that homework is due on the day of the test, or
No, it's the day of the quiz.
only the days of the quiz?
Yeah,
Okay,
so you just concentrate on the test when it's a test day.
got it. Thank you.
Okay, have a good one. Okay, bye-bye. See you on Monday. Bye.
Thanks. See you Monday.